the session. So please be seated. I think we'll start. Okay. So I hope all of you had some coffee. Let's keep moving. Our next speaker is Dr. Richard Graham. Again, he has come to Mug many years. He's a senior director at NVIDIA's networking business unit. His primary focus is on the HPC and AI network software and hardware capabilities for current and future HPC and AI technologies. Prior to moving to Mellanox NVIDIA, he spent 13 years at the Los Alamos National Lab and then Oak Ridge National Lab in computer science, technical and administrative roles, with a technical focus on communication libraries and applications analysis tools. He is co-founder of the OpenMPI collaboration and also was chairman of the MPI 3.0 standardization efforts. So I think I have interacted with Rich since his Los Alamos day, all right?
25 years.
It's 25 years. I don't know if many of you know, there used to be an MPI library called LA-MPI, Los Alamos MPI. That's how we started our collaboration. And when Rich went to Mellanox, we had sustained collaboration and we are still continuing, okay? So let's give a big hand to that.
Can people hear me? Okay. So nice to be back here again. Sorry I missed yesterday. I was in the UK with my wife and daughter and flew in last night for this. So glad to be here and be able to give a presentation. For those of you that remember, probably a lot of people in the room, usually what I talk about here is offloading technologies and the like, because it really lines up with a lot of work that DK and his team have been doing. But today I'm going to talk about something a little bit different. It's still offloading in a way, but not work that I've directly done, where I'm more reporting and talking about our Ethernet capabilities, our Spectrum-X Ethernet capabilities that we've developed, that we being NVIDIA has developed well starting on the order of 10 years ago and more. But it really coming to fruition in recent years. So really the focus of a lot of the work is AI, obviously, because that's where a lot of money is being spent these days. That's where a lot of systems are being bought. That's why prices are going up so much, because there's such a high demand for the components, and the manufacturing capabilities haven't caught up yet. So AI drives a lot of things, but AI is, in my view, is really a part of HPC. I mean, there are different communication. When it comes to communication, there's some patterns that are unique to specific AI type of approaches, but in general, they're really, in my view, AI is an HPC application, one area of applications. So from NVIDIA's networking perspective, from a performance perspective, scalability and the like, InfiniBand is really the golden standard. It provides low latency, high bandwidth. It's very resilient, and it's been demonstrated to scale out to hundreds of thousands of endpoints in a given system. A lot of people don't want to use InfiniBand, right? They prefer to use Ethernet, right? Because it's interoperable with a lot of other systems that they use. And so as a result, you know, because of customer demand, we've put more focus on Ethernet. We've supported Ethernet from the Mellanox days, but really emphasizing it as being the network that many systems will use for their day in and day out work, is what has driven us to use the capabilities that we developed before in the context of InfiniBand, learn the lessons that we've learned from there and incorporate them into an Ethernet solution. So Spectrum-X is Ethernet. Ethernet with every completely, but it has features in it that help with the issues, the challenges that you get when you run very, very large, tightly coupled problems. So NVIDIA's, before creating Spectrum X, our Ethernet solution was based on Rocky V2, still is. And it was used in large deployments. You know, it was good for a lot of data centers. But the challenges that existed before prior, the fact that it assumes nearly ordered traffic. If your traffic isn't ordered, you know, the way it dealt with the out of order was not optimal. Let's just put it that way. And it didn't have as much flexibility in terms of using very, very large radix systems. And so that's where the work on Spectrum X Ethernet started. So it started with the initial Ethernet that existed, and then it built on, and then it improved it based on lessons that we've learned from other large system installs. So to give a bit of background here, just to the sort of things that drove the design. So in a lot of these large AI jobs, as well as HPC jobs and the like, what really determines a lot of times the scalability and performance of applications are these collective operations, which are run very tight, very tightly coupled. You need low latency, you need high bandwidth, even though there's a lot of data flowing around. And so I needed to address those sort of issues. Needed to address the fact that in real systems you have multi-tenancy, you know, and so you have multiple jobs, you know, running all the time. So you're going to have background noise, just the way resources are allocated to users, and so dealing with background traffic was important. And also, as you know, people that run large data centers, things like port flops and stuff like that really get in the way of using the system. And so these were some key features from a network perspective that were the focus of designing Spectrum X. I have some data here in terms of the impact on bandwidth of various traffic patterns. So if you look here, these show the message bandwidth as a function of the time it takes to schedule a packet, right? So and you do these, of course, pipelined, right? So you're not really paying 30 microseconds per decision. But if you're doing adaptive routing or something like that, or if you're trying to load balance somehow, those things cost time. And the more time it costs, the more you lose in terms of bandwidth. And these are just some numbers that are here for demonstration. We have the delay in terms of all-to-all. What's that? Oh, this is queue occupancy. You know how port queue switch queue occupancy is how full are the buffers, and what sort of delay does that give you in terms of traffic. And so you see as traffic gets as the buffers get fuller and fuller, delays get larger, and so performance gets smaller. And here we have the performance of I believe this is an all-to-all measurement. Yeah, it is an all-to-all measurement with background noise. We have Spectrum X bandwidths versus off-the-shelf Ethernet bandwidths. And so, and also we have here information on what happens when links fail. So generally, you can see that you know, link failure with standard Ethernet has been an issue in terms of recovery and other things like this. So let me say one thing here that I should have said up front. so what I'm talking about now is actually in a white paper that's public, right? I've just pulled out a lot of the slides from there, added some background to sort of give some more information. And what's done here, the hardware that's used in these measurements, almost all the data I'm going to talk about are measurements that have been done. There's one set of simulation data at the end that I'll show. The hardware was exactly the same, sorry. And the difference between the measurements is, are we using the base NVIDIA Ethernet support, or are we using the Spectrum-X support, which adds a few features, a few capabilities to the mix. So with respect to the things that drove that drove the design. So first of all, so when you build Ethernet, there's not one Ethernet, right? Different people build different types of solutions based on the audience they're targeting, right? So if you're doing Ethernet for over the WAN, you'll have a very different design. I mean, it's still Ethernet, but different design than if you're aiming at tightly coupled systems. And so what this particular design is focusing on scale out to hundreds of thousands of endpoints for AI and HPC. I mean, this is the big market today. This is the people that are buying these are the people that are buying these sort of systems. It supports both adaptive RDMA and custom Ethernet protocols, customer Ethernet protocols. So MRC is probably the most known. It's the one that's been published. It's not the only one, but it's the one that's been published and well known. It's optimized to support multi-rail and multi-plane. I'll talk a bit more about what these are soon. So it's optimized for environments that are very rich in terms of network capabilities, but also very challenging in terms of maintaining the high level of performance. And it's optimized for both GPU and CPU systems. Just one picture here. Sorry, it's a marketing slide, but generally just to show you this exists today. People use it. People ship, I don't know how many thousands of ship and install thousands of these systems weekly, literally. So the design has been such, there's been a lot of technology that's developed so you can sustain these sort of rate of getting new systems out there. And I will comment about the top 500 is the reason a lot of the systems that are sold don't make the top 500, because if you make the top 500, you don't make money, right? So they have paying customers that need to work immediately. No one's going to waste time to run a top 500 number. The main thing here is you see a nice performance improvement across the board in terms of network performance when you compare the off-the-shelf Ethernet to Spectrum-X Ethernet. So some of the goals for this support is obviously low latency and jitter. These are large systems. Jitter has a major impact on performance. P99, your 99th percentile, is the dominating feature that controls how well your simulations or your jobs will run. And obviously designed for scale, and also designed to get AI as quick as possible. So that's why a lot of the focus on manufacturing and installation processes and stuff like that, to be able to and have very, very well-defined reference design so you can stamp these out at a high rate. So a few of the key design principles is, first of all, multi-plane network design. I'll talk about all these. The topologies that are supported these days, most people prefer fat trees. They have a lot of advantages to them. They're simple, a lot of routes, and so they're really good for scaling up. Processing is on a per packet basis. So every packet gets its own decision in terms of how it goes through the network. Adaptive routing has been added. Congestion control has been improved. And of course, quality of services have been there all the time, but that's one of the things that lets us also get good system performance. So a bit about multi-plane architecture. So before getting to the generation of the Spectrum 4 generation, I think, as well as the NDR and IB generation, when you had data going out of the network, you have four lanes going through the SerDes. A single message would be managed across all those lanes. What's changed in this multi-plane design is your hardware still has 4 or 8 lanes or however many lanes go across the network. But now each of the lanes is managed independently. They're managed, and so you have planes in the network that are independent of each other. And so they can respond independently to each other and do respond independently to each other at the hardware level. So just think of your 4X IB cable that goes out to over the network. Each lane will go to depending, of course, on how you design it, but this is how we design them. Each lane will go to a different switch. And then if you have multiple NICs in a system, which we have in our DGX systems and the like, or other systems that are designed like that, you can also have parallel routes. So you have a lot of routes between endpoint, independent routes between endpoint, which gives a very, very good building block for performance. And the feature and the items that are the capabilities that are used really depend. The capabilities that are used: congestion control, adaptive routing, the plane decision, are all run independent of each other. Right? There's no coupling between them, so the design is very, very clean. When you go into the network, you don't have to have this complex set of considerations to take into account to decide how to route packets. Because if you have to route packets at a very low latency, very high rate, you can't afford something like that. So congestion control, I should say, it happens per plane. So remember, we have each of your nominal wires that go out on the network has at least 4 lanes, 8 lanes, something like that. Each of those runs independently, right? So if you get one plane that starts to get congested, that doesn't mean that all the other 4 planes are suffering because of that one lane, right? So you have the ability to distribute, to deal with congestion on a plane-by-plane. You do deal with it on a plane-by-plane basis, which you don't with the standard Ethernet. So the support for congestion control is split between the switch and the NICs. So there are things that have been added in the NICs, for example, to help with congestion control. There are probes that are sent onto the network to help detect when the network itself is becoming slow. They run at a very, very high priority, so they get through because they're critical to system performance. They're not frequent, but they're frequent enough. There's the standard ECN markings that also get interpreted by the endpoints. And it's marked by the switches. And so this high, this large degree of freedom lets one adapt fairly quickly to congestion, right? Congestion is always reactive, right? So you want it to be as quick as possible. So there's a cartoon here, how things initially, you start with, you have basically you can control how busy things happen at the endpoint. So if you see endpoints that are congested, you'll if you send data to other networks, other routes, then at some point adaptive routing starts getting kicked in, and when that still doesn't have help, then it goes back to a congestion control from the endpoints. So in terms of the multi-plane load balancing, so this support is hardware level. It's not software. Software would be way too slow to respond. Software doesn't really have the full range of understanding of multiple jobs running on the system, which hardware does. It on a packet per packet basis, it will take into account several factors in terms of determining which route to take a packet, to send a packet. So here's just a cartoon of a QP that's generating a packet. So it has four planes that can pick from. 2 planes are problematic. One is rate limited, probably because congestion control or something like that. The other maybe had a port flop, and so it's not able to absorb. No data can go down that line, and then it basically has two planes that are possible to use, and it will pick the one that's least congested. So it'll pick if I understand it'll pick P0 if I remember correctly. Yeah. No, it'll pick P3. It has only one. Green is the occupied one, so it'll pick the one that's least occupied to get the packet out that. So this is really done on a packet per packet basis, very, very fast in terms of latencies. It's a few tenths at most of nanoseconds. I don't remember the numbers, but it's very, very fast. I put this up here just so people can go back and look later on at the data. Again, this is a paper that's publicly available. I think I forgot to put the link on it, but before DK, I give it to you, I'll point you to the link. But this describes a system where things were run. So I have about 5 minutes, so I'll run very, very quickly through actual numerical results. So these are real results. Looking here, first of all, at latency on a 64 nodes using 64 endpoints. So a few things we see in terms of, so this is from an all-to-all measurement using nickel. It was run with ConnectX 7, and 16 victim nodes and 48 nodes are generating background noise. So we see in terms of latency, when we use, so the difference between the measurements, HPCX uses the HPCX measurements, you use a full HPCX feature set. The off-the-shelf Ethernet shuts off the HPCX features. It's the same hardware, but you're not leveraging the ability. You're using sort of off-the-shelf Ethernet capabilities. So we see, first of all, on latency, the latency is very, very tight. This reports the average and 99 percentile, but you can see that they're very, very close to each other. I don't remember what the message sizes here are. It's not listed on I don't see it on the slide here. Versus standard Ethernet, so 400 gigabit per second is line rate. So we're getting very, very high rate with respect to line rate. It's over 90%. I don't remember exactly how much it is. Standard Ethernet, the average is lower, and there's a big tail effect. So this tail effect is what will really impact your end-to-end performance, especially when it comes to collectives. In terms of 99 percentile, I'm sorry, this was bandwidth. This is latency. Latency is with Spectrum X Ethernet is lower than off-the-shelf Ethernet, roughly a factor of not quite 2. It's not as tightly bound as the bandwidth is. And you can, we can say why it is. Versus, again, the latency for standard Ethernet is higher, more spread, and the like. So, so it's doing what we expect. This is not an 8-byte message. It's probably a 4 kilobyte message. I'm not 100% sure, but it's certainly not an 8-byte message. Looked a bit at the impact of basically congestion control on performance. So this is around 16 nodes of DeepSeek v3 with and without background. So it's 16 nodes. When there's noise in the background, again, there are 48 nodes in the background generating noise. And the main thing we see here when we compare Spectrum X Ethernet to off-the-shelf Ethernet is when there's no background noise, their performance is similar. There's some noise up front here, which is not, this is not abnormal for these sort of measurements. I can only guess what it might, guess that it might have to do with congestion control, but I'm not sure. Well, because this is an all-to-all measurement, so this is probably some congestion control. Taking a while for the system itself to get equilibrated, and then once you turn on background noise, you see that with Spectrum Ethernet, there's not much change. It deals with, there's so many routes and things since things happen packet by packet, you can respond quickly and get about a factor of close to 2 improvement in the application performance. Sorry. Here, just briefly, because I'm running out of time, this is performance, ideal performance on that particular system. So what's running here is, again, a nickel all-to-all with 16 victim nodes, 48 background nodes running, generating traffic on the network. This is what you would ideally get. This is the maximum you can get out of the network when you have 5% link failures, 20% link failures, and 75% link failures. We see that Spectrum X, as the number of link failures increases, Spectrum X is recovering a lot better than off-the-shelf Ethernet. But again, that's this flexibility in terms of how you can respond. Similar set of data for actually generating explicitly shutting down links for a period of time and seeing how this impacts the overall runtime of the application. This one happens to be a Nematron 3 job, and we see that the original time steps, that is the ones that don't have the yeah, these are the time steps, and this is how the running average changes as you get host flaps. So you can see that the performance tracks the original simulation run times, even with the link flaps, and they generate link flaps both on the host as well as in the fabric itself, as well as in the switches themselves. Last set of data is basically looking some more at load imbalance in or asymmetry in the network. I'm out of time, so I'll just give one slide here. So we can see that this is an all-to-all. This is actually a simulation, if I remember correctly. Yeah, at least some. I'm sorry. The first 3 are measurements. The last one is simulation. So here is a one-to-many pattern. With and without using with and without background noise. So without, so we can see that again, as Spectrum X reacts well to background noise and asymmetry in the network versus standard Ethernet. This data is for all-to-all, and again, we see a big difference between runs that are congested and are not congested, and this gives how fast the network performance is recovering with Spectrum X. So it's a ratio of this is probably the all-to-all, a ratio of the run with congestion and without congestion. So you can see that as message sizes get fairly large, even for small message sizes, the loss is not great. But as you get to larger messages, the system has time to equilibrate. This is basically a comparison of a simulation of the performance of the bus bandwidth, actually measured for an all-to-all measurement with Spectrum X and the congestion control that Spectrum X uses, and an ESR-based congestion control. It's been suggested here recently, so we can see good performance. So that's it. I'm about 2 minutes late. Sorry.
Okay, so let's give thanks to Rick. Well, we have time for a few questions. Any questions? Okay, multiple things. Okay, we can go.
Thanks, Richard. A very good presentation. I was wondering for long-haul RDMA, there is the RTT for that is going to impact the performance of RDMA.
That's right.
So if you were to do a scale across, what is the requirement in terms of latency and throughput to sustain similar performance as your scale out, something like that?
Yeah, so what we do, and I'm vaguely familiar with it, not extremely well familiar. Obviously, you need more buffers, right? But that's actually, having a lot of buffers is actually a bad answer, because it ends up generating a lot of stuff at the endpoint. And so what's used, if I remember correctly, I'm trying to remember because I read about what was done and I don't 100% remember, but they basically are using a different set of congestion control parameters. How is it they're doing that? I don't remember how. I'm sorry, I don't remember the details. But they do have a separate the congestion control is controlled by pairs of endpoints, and so they have for distant endpoints, they use a different set of parameters to manage the congestion. If I remember correctly, they end up getting a pretty high percentage of network bandwidth. Jitin, you wanted to say something. Oh.
Can you press that? Yeah, and then talk. Yeah.
Have to. Sorry. Yeah. So I was just saying, like, so we did this collaboration together, right? The SC paper last year. So what we did was we do the erasure coding and then send across, and we have like some NVIDIA exposed some like new APIs to like signal this much earlier and give that feedback to the user, like, oh, which of the ones are actually available versus not, and retransmit only those if needed, right? I mean, again, we cannot really rely on RTT-based designs for extremely long scale, right? So that's why we fall back to this EC. So yeah, software and hardware, like, I mean, NVIDIA exposed those NIC level features, yes.
And I think there've been some improvements over the last year or so too in what they've seen.
Sure. Yes.
Yeah, I think, yeah, what they do. Yeah.
Yeah, might be one more question and then we'll switch. Or okay, let's yeah.
So my question is, what's the best practice for the detection for the networking failure with Spectrum X?
So from what perspective do you ask? So Spectrum X does everything in hardware. So Spectrum X, so the hardware knows very quickly when a port, for example, is not available, because it marks it as not available.
Yeah, the question is more about like if there's a link flapping or link failure, how we can detect it as soon as possible, or how we can deal with those kind of failure.
From the application level?
Is that fast enough?
No,
or-
you don't want to use, the application is way too slow, right? Because you have to have it, not only does it have to go through the network, it has to bubble up at the software level. The software level has to understand something. Software level has to hope that by the time it makes a decision, things haven't changed. And so the best practice is to leave it to the hardware. Because the hardware will deal with retransmissions if you're using a reliable protocol. The hardware can detect at network times of network speeds when something has gone bad. It will slow down, right? But if you notice, the slowdowns were really minor compared to what we're used to historically, right? Because it is happening at network speeds.
Yeah, I just heard of some solution from NVIDIA is what just happened. I'm asking maybe there's anything new or something.
No, there's nothing new since that.
Okay,
No,
thank you.
No, not that I'm aware of, I should say.
Thank you.
Quick question and we'll switch.
Feel free to stick to the NVIDIA official answer, but what is NVIDIA's relationship with Ultra Ethernet nowadays? Because I know you guys joined the consortium and it sounds like have mostly been kind of watching from the sidelines, and we've all been speculating why that is, but do you have a answer on
I'm
that?
not participating in that process, so
Okay.
I can't really tell you why.
Okay.
No, I mean, the world is so Ultra Ethernet, if it makes good business sense, we'll support it, right? We support multiple versions of Ethernet today that are very, very different in characteristics, lossy versus lossless. There are certain routes that we've taken based on our experience, but again, if customers want things, we're serving customers, right? We're not doing stuff for ourselves, and so if there's a demand for something like that, of course we'll support it.
Okay, so I think with this, we'll switch to the next talk.